orbital diagrams are a way of showing where the electrons are in an atom. So we know that the most stable location is going to be as close to the nucleus, right? Because the electrons are negative, the nucleus has the positive protons, the attraction pulls them in. And so the first energy level, that's where the electron's going to go first. So in the first energy level, there's the 1s, right? There's no P, D, or F in the first energy level, just the 1s. And any s subshell has one orbital. So we use a box or sometimes a line to represent each orbital. Right, so how many electrons could possibly fit in that orbital? 2. And so the orbital diagram way to show that is to put the 2 electrons in where we use an arrow to represent each electron. You might see a full arrow or just like a half-headed arrow there. An arrow pointing up represents an electron with an ms quantum number equal to 1/2. And so what we find is if 2 electrons are going to be in the same orbital, they can't have the same value for ms. So my second electron in that orbital has to have ms equal to a negative 1/2. Right? It's not possible for 2 electrons in the same atom to have all 4 quantum numbers equal. Right? So if I were to look at the quantum number for this first electron, n is 1, L is 0, ML is 0, and ms is 1/2. For the other electron in that orbital, it has the same values for N, L, and ML, because those values tell me about the orbital and energy level. And so if they're going to be in the same orbital, they have to have different values for ms. So if the question about orbital diagrams is what is actually impossible, there's only 2 things that are impossible. And that is to put 2 electrons in the same orbital with the same spin, or to try to somehow fit more than 2 electrons in an orbital. Those are the only things you cannot ever do in an orbital diagram. Anything else is either ground state or excited state, where ground state means that's the most stable way to put the electrons you have into the atom. Right? So if I have 2 electrons, the most stable way to put them in is to put them both in the 1s. That's ground state. So in excited state, there are many possible excited states. There will always be many possible excited states. So above the 1s, there's the 2s. And there's the 2p. And the 2p is a subshell that has 3 orbitals. So I divide my 2p subshell into 3 total boxes. So if I have an atom with 2 electrons, and it's in a ground state, both electrons can be in the first energy level. If I have an excited state version of that, I could take either one of those electrons and move it to a higher energy level, the 2s, or any one of the 2p's, or any other orbital that's out further from that. So if I want to show an excited state, I just move the electron up to a higher level. So when we're thinking about an excited state, that's anything that is possible, meaning it doesn't break these ideas around what's impossible, but not ground state. And so there's some rules. There's Hund's rule and the Aufbau principle, which we'll talk about to help guide us to drawing the ground state configuration or the ground state orbital diagram. So that following those rules, when I put electrons in, let's say this would be my ground state if I have 2 electrons. If I wanted to draw an excited state, I would just take one of those out and put it in one of these other orbitals. That's one possible excited state. So what if I wanted to have a ground state for a situation where I had 4 electrons? So I could draw it like this. Is that a ground state? No, that's an excited state. Why? would go in an orbital where there's already an electron. Wouldn't the two electrons in the same space with all their negative charge start repelling? Wouldn't that make it less stable? Right. So to an extent, putting two electrons in the same orbital does make it a little bit less stable because they are in a space where they have to get kind of their electron densities kind of overlap, and that causes some repulsion. But the idea that we can fit two electrons in an orbital is generally the idea we want to follow, because that helps us to recognize that as long as I don't put more than two, then the repulsion of those two electrons in the same orbital is not so great that it becomes more of a factor compared to the idea that we want the electrons to be as close to the nucleus as possible because they're attracted to the nucleus. Plus, when they're in the same orbital with opposite spins, the spinning electron creates a magnetic field, and the opposite spinning electron creates the opposite magnetic field, and that creates a slight magnetic attraction, which helps to compensate for some of the electrical repulsion between the negatively charged electrons. So this would be an excited state. To make a ground state, I would have to, for 4 electrons, I have to pack them in. So the idea there is, I want to fill up a subshell before I start putting electrons in the next subshell. And then I want to fill that up before I go to the next subshell. Because as long as they're in the same orbital with opposite spin, they have a little bit of a magnetic attraction to offset some of their electrical repulsion. Plus, the 2s, on average, is going to be significantly closer to the nucleus than the 2p because of that spherically shaped s orbital versus the more elongated shaped p orbital. And so the electrons are more attracted to that space that's closer to the nucleus. So once I start packing electrons into a subshell that has degenerate orbitals, meaning I've got multiple orbitals in a subshell that are all the same energy, then they want to spread out and avoid repulsion. Right? So in the 2p, there's the 2px, 2py, and 2pz, right? What's the difference between those three? There's no difference between them in terms of their size or shape. It's a difference in spatial orientation, right? So if I'm thinking about my coordinate system, the XYZ plane, the 2px is on the x-axis, the 2py is on the y-axis, and the 2pz is on the z-axis. Which of those 3 orbitals stabilizes an electron better? None. They're all the same, right? If the electron's in the 2px versus the 2py, what's the difference? It's just spatially it's on a different axis, but it's still on average the same distance from the nucleus, so it's still equally stable. So when I have 3 equal energy orbitals, because the only difference between them is their orientation in space, if I start putting electrons in that area, it doesn't matter which orbital I put electrons in. So because in the Western world we do things from left to right and we do things from top to bottom, you will usually see the first electron in the left-hand side pointing up. That doesn't have to be that way. To be ground state, I could put that first electron in any one of those boxes pointing either up or down. It's still ground state. So if I have 5 total electrons to put in, because maybe I'm dealing with boron, which has 5 protons and needs 5 electrons to be neutral, if I know I have 5 electrons, that 5th electron could go anywhere. Maybe I put it here pointing down. This is an example of the ground state electron configuration for boron. Non-excited state is I build up the subshells first, and then this subshell has 6 spots in it, and I only have 1 electron. I can put it in any one of those 3 orbitals. They're all equal in energy. But once I put 1 electron in, now as you said, there's a difference in energy for the next electron if I put it in the same orbital versus if I put it in one of these other orbitals. So that's what we're going to talk about today, but what we'll find out is the next electron. So if I have 6 electrons to put in, the next electron can go in this orbital pointing in the opposite direction from the first one because that does not violate our rules about what's possible. This is possible, but it's not a ground state. This will be excited. Why? Because I've got the two electrons in the same orbital, right? So I've got these three options on the three different axes, 2px, 2py, 2pz. And if I put one in the 2pz, that's a certain area in space where that electron density is going to be. I have more electron density to put in. I don't want to put it in the same area. It's going to cause some repulsion. I want to put it in one of the other open areas that's still the same distance from the nucleus. So to make the ground state, I have to take that second electron. If the first electron was pointing down, I have to take the second electron and put it in either one of the other two also pointing down. So this would be the ground state. One possible ground state. So for the ground state, if I have 6 electrons, the 2 electrons in the 2p have to be pointing in the same direction, either both up in any combination of these except for not in the same orbital, or both down in 2 separate orbitals, now also not in the same orbital. Questions about that?
Shouldn't there be a down one in the middle? Or each
Not
right?
if I only have 6. I'm only putting 6 in. Right, yeah. So then if I have a lot more electrons, let's say I've got a bunch more electrons, so I start putting the electrons in, I'm filling these in. In the 2p, I've already put 2 in, so the third one, again, should be in a separate, if I have another electron to put in, I put it in a separate orbital so it doesn't repel the other ones. Once I've filled up each of the orbitals that are all equal in energy, if I have another electron in, I'm not going to go to the next subshell because there's still space in the 2p, which is closer to the nucleus on average than the 3s. So I'm going to take my next electron and put it in one of these, spinning in the opposite direction from the one that's already there. And then if I still have more electrons to put in, I fill up that subshell. Once the subshell's full, and I filled it up, there's no more space in that area, now I have to go to the next subshell. So if I go to the 3s, fill in electrons here. If I still have more to put in, then I go to the 3p. So again, I want to spread them out first with the same spin. Doesn't matter whether that spin is up or down, as long as they have the same spin and they're spread out. That's ground state. Then I can complete it. Then actually, after the 3p comes the 4s. And then the 3D. The 3D has 5 orbitals, so I need 5 boxes. The 4s has 1 orbital, so I need 1 box. And so if I'm looking at a ground state element right now, so far I've added 2, 4, 6, 8, 10, 12, 14, 15, 18 electrons. So if I don't have any electrons in the 4s or the 3D and I have 18 electrons, as a neutral atom, I'd be talking about argon. Right? So that would be argon's ground state orbital diagram. To make an excited state version of argon, if I wanted to make 18 electrons and make it an excited state, what could I do? I could take any one of these electrons that's already in there and move it out to one of these other levels. That would be excited. So there's dozens and dozens of possible ways to make an excited state atom. Another way, well, not for argon, but I'll mention that in a minute. So if I go beyond argon, talking about these next elements, I have more electrons to put in. I should start by putting them in the 4s rather than the 3D. The reason for that is because the 4s is spherical. How many nodes are there in the 4s? 3 nodes. Good. The 4s, 4th energy level, it's a spherical shaped orbital, and it has 3 nodes. Each of those 3 nodes is spherical. So there's one spherical node kind of close to the center, another one here, another one here. In between those nodes, there's electron density. So in the 4s, it's kind of like a multi-layered orbital with multiple layers of electron density. Right, so if the nucleus is here, there's some electron density close to the nucleus, and then there's a node. More electron density, another node. More electron density, another node, and then more electron density outside of that. So when an electron's in the 4s, it's got some electron density pretty close to the nucleus, but on average, most of its electron density is further out, right? Its energy, or the stability of an electron if it's in the 4s, is going to be associated with where its average electron density is located, the average distance that electron density has from the nucleus. So if we compare that with the 3D, because the 4s is spherical, and because there's some electron density right next to the nucleus, if I have an empty 4s and an empty 3D, electrons should go into the 4s first, mainly because of probability or density of electron negative charge being able to get close to the nucleus. If I look at what the 3D looks like and kind of overlay that, there are 5 3D orbitals. 4 of them look like 4-leaf clovers, so that would be like one of them. So in a 3D orbital, there's 2 nodes, one here, right? And then 4 of the 3Ds are 4-leaf clover shaped, and they are on different axes, 3-dimensionally. And then that last one is like a double lobe with a donut. But those are all equal in energy, right? So the 5 3D orbitals are equal in energy, but if I look at them and think about where the average distance from the nucleus, the electron density would be in the 3D, it's very similar to the 4s. Because the 3D shape is relatively elongated, but in the 3D, there's not much electron density right next to the nucleus, although in the 4s there is. So they're kind of really quite close. So if I'm putting an electron in, and it has the option to go in one of the 3Ds because they're all empty, or in the 4s because it's empty, usually it should go in the 4s, and there's 2 exceptions we'll talk about later that you need to know to that. But if the electron goes into the 4s, you should fill that up first. Now I have 5 3D orbitals that are empty. So if I'm continuing to put electrons in, they would go into the 3D. So let's say I was looking at titanium, and I wanted you to give an excited state version of titanium. There's lots of different ways you could do that, right? The key thing would be to make sure you've got the correct number of electrons. So if I say it's a neutral titanium atom, titanium by definition has to have 22 protons. It's neutral, it must also have 22 electrons. So right now I've put 20 electrons in. I need 2 more electrons, so I'll just put them in. So if you want, you can start with your ground state electron or orbital diagram, and if I ask for an excited state, all you have to do is take one of the electrons and move it out to another level. So if I make it, this is my ground state. If I want to make an excited state, is this an excited state version of titanium? Nope. This is not an excited state. I have 2 electrons. They're in different orbitals that are equal energy, and they have the same spin. That's a ground state. Right? So if I'm comparing the electron being in this position versus in this position, there's no difference in energy. Those 5 orbitals are equal in energy. Okay, so you want to get away from your Western world bias, where everything starts on the left and goes to the right for a reason. There's no reason why my first electrons have to start on the left-hand side. That's just a silly convention. These 5 orbitals are equal in energy. If I have 2 electrons, I can put those 2 electrons in any 2 of those 5 orbitals. As long as they have the same spin and they're not in the same orbital, that's a ground state. So if I want to make an excited state for titanium with 22 electrons, I could do this. That would be an excited state, because now it's a little bit higher in energy when the 2 electrons are in the same orbital, but they don't have to be because there are other equal energy orbitals right nearby that they didn't go into. Is this an excited state for titanium? Correct. That is not an excited state. It is not a ground state. It is impossible. So I can't do that. Is that an excited state for titanium? Yeah, for sure. Right. I've moved an electron from the third energy level in the S, which is on average close to the nucleus, to an area in the third energy level, the 3D, that's farther out from the nucleus. Is that an excited state for titanium? No, that's a ground state. Again, as long as I'm separating them and they have the same spin, that's a ground state. So one more. What about this? Is that a ground state for titanium? No, that's an excited state. And so the ground state, if I have equal energy orbitals and I have more than one electron to put in there, I have to put those electrons in different orbitals with the same spin before I start pairing them up. And what I've done here is I've put them in different orbitals with opposite spin. That's not going to be a ground state. That's going to be an excited state. Questions about that? Yes. Yeah, so we're also going to talk about that today, but the quick answer is you have to know how many total electrons there are. Right? So if I'm giving you an element, I have to tell you what element it is and what the charge is on the element. So if I tell you it's calcium and it's neutral, then you know with 20 protons it needs 20 electrons. So you would just, then you have to know the order that these go in, so that you can fill the 20 electrons in a way that puts them in as close to the nucleus as possible before you go to the next level and make the electrons as stable as possible. If I'm asking you for a ground state. If I'm asking you for an excited state, you just need to make sure there are 20 electrons total and that you haven't done either of these impossible things, and that it will be by default an excited state. So that's it's hard not to make an excited state. If I tell you the element and I don't say it's neutral, but I give you some other charge, then you have to adjust the number of electrons to give you that charge. So if I say it's a calcium +2, if it's a calcium atom with a charge of +2, by definition, calcium has 20 protons. That's what defines calcium as an atom with 20 protons. So if it's a +2, how many electrons would it have? 18, right. So 20 positive charges, 18 negative charges, balancing them out, comparing them, that's a net extra of 2 positives. That's what would give the calcium a +2 charge. So finally at 18 electrons, I would have to take 2 out from the normal number of, I would put the normal number in and then I would take the outside ones away to end up with the number of electrons remaining that is most stable. You don't have to, you don't have to memorize that this goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, etc. That order is on the formula sheet. There's this chart. This chart right here, it looks like this. It's on the formula. And these arrows are here to tell you how to fill this out. So the way that you would use it is to, anytime an arrow ends, you connect it to the next arrow on the next line. Right, so the order is 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, then 4d, etc. Right? So you don't have to memorize that order. All you need to know is when you have a 3d, that has 5 boxes. And so if you're trying to fill electrons in there, you want to follow the guidelines to fill the electrons into that boxes. So you need to know how many electrons you have to put in, how many boxes are in each subcell, and how to distribute those electrons in the boxes. Correct. Yeah. F has 7 bonds. Other questions? Yeah. Yeah, can I look? So in question 15, on the practice exam, this is a question where I ask you to determine how many protons, neutrons, and electrons are in an atom. So A is pretty straightforward. So let's look at B and C. So you have a bromide, 79, and a titanium, 44. So in these, the number of protons is automatic once you know the element, because an element is defined by the number of protons. So bromine, by definition, has 35 protons. Titanium, by definition, has 22 protons. So the number on the periodic table, that's not the decimal, the whole number one, that's the atomic number, that tells you how many protons are in the atom. So then the neutrons and protons added together give you the mass. So we can recognize that, since the electrons are super light, they have virtually no matter in them. They don't really add to the mass of the atom. So when you have an isotope given that has a certain mass, you can plug that in here, subtract the protons from that mass, and you already have determined, and you can figure out the number of neutrons. So we would take, for bromine, 79 minus 35, and we get 44. And for the titanium, 44 minus 22 gives me 22. So then there's another formula which we didn't really mention, but that is that the protons minus the number of electrons will equal the charge. Right? Because the charge that's given, which is here, the charge tells you how balanced or imbalanced that atom is in terms of the charged particles that are around it. Right? So if I have no charge shown, I assume that the atom is balanced and the number of protons and electrons are equal and they're balancing out. So if there's zero charge, that would result from the number of protons be equal to the number of electrons. So if it were 10, it'd be 10 minus 10. That gives me zero charge. If there's extra electrons, then I need to subtract that number because the electrons are negative. So if I have 10 electrons, or 10 protons and 11 electrons, if I subtract, I would end up with a negative 1 charge, which is what I should have if I have more negatively charged particles than positively charged particles. So a common mistake that students make is when they see the charge, they think that that is the adjustment to the number of electrons. That's not how you want to think of it. A plus 4 charge doesn't mean I'm adding 4 electrons. A plus 4 charge means when I look at the number of protons and electrons and look to see which I have more of, I have more of the positively charged particles. That's why I have an extra positive charge on my atom. So if I know for the bromine that I have 35 protons, and I want to know how many electrons I have, whatever that number is, and I know the charge is minus 1, I can plug those into the formula. Or I can just work that out of my head and say if I know I have 35 positive charges, I have to have 36 negative charges end up with one extra negative. So that would be 36 electrons. And for the titanium, I could apply the same formula, 22 protons minus some number of electrons gives me an overall plus 4. So if I solve for this value, algebraically, I recognize that I have to have fewer electrons than I would normally have for it to be balanced. So I'd have to have 18 electrons. Yes?
Are we allowed to use a periodic table on?
Yeah, you should bring a periodic table. If you don't bring one, you can use this one. But if you can't see it, you'll have to keep coming up here. So I would definitely bring one, print one out. Other questions? Yeah, you should bring something to write with, a periodic table and a calculator. You don't need to bring the formula sheet. That will be attached to the exam.
That's 22 minus whatever electron number it is equal 4.
Yes. 22 protons minus the charge will be equal to the number of electrons once I rearrange that using some algebra. That's where I got 18. 22 minus 4. Other questions? Yeah, sure. Yeah, good. So yeah, let's talk about isotopes. So for the exam, in regard to isotopes, there's a couple different ways you could see a question related to the abundance of isotopes and the mass on the periodic table. The most one way is I might give you some isotopes and ask you to calculate the average. So I might say, I don't know offhand, but I might just pick an element and look up online what the isotopes are and what their natural abundances are. So maybe I would look up iridium. And I might say iridium has 3 isotopes. So maybe iridium has 191, 193, and 194. I have no idea. I'm just making this up. So in one scenario on an exam question, I might give you the isotopes and I might tell you their natural abundances, 35%. Actually, let me make this. What the heck was that? So maybe this is 72%, 15%, and then maybe the other isotope is 13%. So if I ask you to calculate the average, the way to do that would be to multiply these percentages, convert them into fractions. So it would be 0.72 times the 191 mass. And I would add to that the fraction that the second isotope contributes to the average, which would be 0.15 times the 193 mass. And then I would also add the 0.13 times the 194 mass. And that would give me the average, which should match the average on the periodic table. So on an exam, I probably wouldn't give you an actual element. I might give you a fictional element. That way you couldn't just look on the periodic table and write down the average. And yeah, you'd have to actually be able to use this method to find the average.
Make sure I'm reading this right. JP, what is that below it?
Huh?
Is that a little 3% above the 72%?
No, I crossed that out. Somehow there was a problem with the pen here. So these are iridium atoms with 3 different isotopes. So 72% of iridium is the 191 isotope. 15% is the 193 isotope. 13% is the 194 isotope. So that's one way you might see an exam question related to isotopes. Another way is I might actually use the periodic table and I might say something like iodine has 3 isotopes. I would actually look up some information and get the actual information so the question makes sense, but trying to make up a question off the top of my head, I might say something like iodine has 3 isotopes, 127, 128, and a third one. What might the third isotope be? Something like that. So in this particular one I just made up, there's more than one possible answer. So as long as you came up with a number that made sense, that would be okay. So what can we say about these are not the actual isotopes of iodine. I made these up. But if these were the isotopes of iodine, what could we say about the third isotope? Where would we look to get information about what the third isotope might be? We would look on the periodic table, right? Because iodine's average mass, based on the natural abundances of the 3 isotopes, on the periodic table is listed as 126.9. That's the average mass. So if the average is just below 127, and the isotopes I gave you are both 127 or above, then this third one has to be what? Less than 127. In order for the average to be less than 127, I need to have something less than 127 to cause the average to go down below 127. Right? So you could put 126 here, you could put 1.5, 1.4, something. It probably wouldn't. You wouldn't want to put 5. That's not. You're going to have some number of neutrons that's going to be at least somewhat close to the other isotopes. It'll be in the 120 range somewhere, but it definitely would have to be 126 or below to make sense in order for me to get this average that's on the periodic table. So those are the types of questions I would give you. I'm not going to probably give you the isotopes and ask you to calculate their natural abundance. Let me double check that when we take a break. I'll pull that up and double check it. Any other questions before we take a break?
What was that thing again? The 9?
What might the third isotope be?
Okay.
Other questions? I didn't mean to imply that we were about to take a break. Sorry. Do we have time for more questions? 3.85? So 3.85 asks you to kind of compare and contrast the 1s orbital and the 2s orbital. So what they have in common is that they're both spherical. So we know that any s orbital is going to be spherical. The difference is that the 1s is going to be a more compact sphere and the 2s is going to be larger. That's the main difference. Again, keeping in mind that the outside barrier of that sphere is based on the idea of including 90% of the electron density inside of the sphere. And so the 2s includes the same space as the 1s, but more, because if I want to get 90% of the electron density of electrons in the 2s, I need a larger sphere to encapsulate all of that electron density. What's the other difference between the 1s and the 2s? Yeah, we could look at the potential energy, lower in potential energy, higher in potential energy due to the average distance from the nucleus that the electron density is. Good. 0 nodes in the 1s, 1 node in the 2s. Can't really think of any other differences, so those are the things I'd be looking for. What other questions? Sure. Yeah. So the terms intensive and extensive refer to types of properties. And the properties of the substance are something that's observable or measurable. So when you're categorizing types of properties, they're usually categorized based on how you make the measurement. Right? So physical properties are properties where you can make a measurement or observe this property without changing the chemical structure of the substance. Right? So we know that atoms sometimes bond together and form compounds. So a physical property you would measure without breaking up the atom's bonds in that compound and converting it into a different compound. So intensive and extensive, those could be physical or chemical. So it's not necessarily related to whether the properties are chemical or physical. The intensive versus extensive relates to when you measure the property, would the measurement you make be different if you had more of the substance you're dealing with? So in an intensive example, having more or less material present does not change the result of the measurement. Because those are like inherent based on what the identity of the substance is. It's in the substance. It's something in the substance that gives you a measurement regardless of how much of the substance you have. So if I have a lot of water versus a little water, it's the same density. Right? Water has the same density whether I measure 5 milliliters of it or whether I measure 2 milliliters of it. But volume is extensive, because if I have 5 milliliters of water and I measure the volume, I get a different number than if I measure the volume of 1 milliliter of water. So that the volume of a substance is not inherent in what that substance is made out of. It depends on how much of the substance you have. That makes it an extensive property. The property is more based on external factors, not factors that are internal to what the substance is made out of. So that's a difference. Intensive, things like density, temperature, melting point, boiling point, things that are based on what the substance is, not how much of the substance you have. Extensive, the actual number that you calculate or the measurement itself changes depending on the quantity of material. So the mass, the volume, things like that. Distance, size. Other questions? Yes. Yeah, so number 12 on the practice exam is an experiment where early scientists showed that atoms are made of both negatively and positively charged particles. And number 13 was about showing that an atom is mostly empty space with a densely packed matter in the center. So in this question, I'm asking you to describe the experiment, not just like name the experiment. So the first one, the main experiment we talked about for this first one was the experiment where they had this radioactive chunk of matter, and it's giving off radiation. They focused that radiation through a small hole. Whoa. Then they put charged plates here. Right, so they've got matter that's naturally breaking down into the pieces that make it up. And those pieces are just flying out with a fair amount of speed. And so if they put these charged plates here, they don't make them supercharged, they just charge them up a little bit. And those charges caused an attraction to the particles that were flying out of the matter. Right? So some of these particles flying out of the matter got attracted to the positive plate, and some got attracted to the negative plate. And so they put a screen here, and they could see where the energy of those particles is hitting the screen because the screen lights up. So that shows that matter is made of both positively charged particles and negatively charged particles, because some of the particles coming out of the matter were attracted to one plate and the other particles were attracted to another plate. Also, by the way, in that experiment also showed that something was going straight through and not moving at all. So there's some type of energy also coming out of the atom that didn't have any charge. So there's not really like a name for that experiment, it's just an experiment. For question 13, though, the Rutherford Gold experiment was the key experiment that elucidated the idea of a nucleus and showed that the matter in an atom is almost exclusively packed into this tiny area in the center, surrounded by mostly empty space. And the idea there was that they used a gold foil, which was only a few layers of atoms thick, and they shot these alpha particles, which are really tiny. The alpha particles are one of the forms of matter that came out of this other radioactive element as well. And based on the speed that those alpha particles are coming out and how much they were attracted to the negatively charged plate, they could calculate that the alpha particles have a positive 2 charge and a mass of 4. So mass of 4 AMU and a positive 2 charge means that each alpha particle is composed of, well, it's too small to see. Too small to write. Each alpha particle is composed of 2 protons and 2 neutrons. So they shot the alpha particles. There are many of them, and they're all coming out. And they were shot at this gold foil. And so what we saw when we talked about that was when an alpha particle comes in, if it doesn't get close enough to any of the nuclei of the atoms in the gold foil, it goes through. But then if it kind of approaches one of the gold nuclei, because the alpha particle is positive and the gold's nucleus is positive, that would cause the alpha particle to be deflected. If the alpha particle goes through in an area where it's not close to any of the nuclei, then it's not deflected. So they were able to calculate, based on how many deflections there were, the angles of the deflections, and how many particles weren't deflected, they were able to show exactly how much empty space there is around each gold atom, how tiny the nuclei are, and how much that causes deflection. So they could calculate pretty precisely, based on all the deflections and the angles of the deflection, that the atoms were not this plum pudding model where all the charges are just spread out evenly in the atom. All the mass and charge is right in the nucleus, and that's what causes those deflections of the other positively charged alpha particle. Because if the particles didn't hit the nucleus, they would go right through. And I don't know why I made this line so crooked here. That was not intentional. This should have been straight. So those experiments you should kind of have the basic information on, so you can describe them in the context of me asking about what those experiments tell us about the nature of matter. What? Not necessarily. Your description could be adequate without a drawing, but using a drawing is helpful to illustrate your point sometimes. No, I'm not too concerned with names of people and things like that. I mean, I wouldn't probably care about. I'm not going to ask you what was the name of the experiment that showed the nucleus existed. I'm much more concerned that you can describe what's happening with matter than remembering the names of things. If you don't know the name of it, and I ask on the exam question for you to describe the Rutherford Gold experiment and what information came from the Rutherford Gold experiment, and you don't know what that means, then that might be a problem. Any other questions? All right, well, since we talked about orbital diagrams, let's just do this quiz real quick. It won't take long. You guys are experts now. So do this quiz, 3-part quiz, and turn that in, and we'll have a break.